Android internals, writing performant native code. If you haven't heard enough about me already, I have spent 5+ years talking to developers just like you around the world, and it is awesome to be here in Hearst. And I've spent 15 years as a software developer before doing that, so I have a little bit of street cred. I actually started developing Android right around Android 1.1. Seriously, actually, I started developing it commercially then. I was working with it ever since 1.0. I wear a lot of hats. This is like one of the smallest hats that I wear. And I have no shame. And I think I'm kind of funny sometimes, especially with lack of sleep like now. All right, performant is an entirely invented word. It is not a real word. How many of you knew that performant wasn't a real word? OK. Good. I got a bunch of English majors here. That's awesome. So and actually, according to Urban Dictionary and most of the research that I did, because I do extensive research on a talk like this, performant was actually invented by software developers. OK, and there's some theories behind this, but the Urban Dictionary defines it as having adequate performance. And but really, this would not be nearly as cool of a talk. Native code having adequate performance. So this is why the word was created, OK? It just doesn't have the ring to it. We don't like adequate in our industry. We like awesome. So rather than title it that, I use the invented word. And we're going to be talking about really, really tiny benchmarks. Because in order for your app to actually perform well, you have to do everything and make sure everything happens within 16.67 milliseconds. That is how you get 60 frames per second. But most of the benchmarks that I'm going to be talking about in this lecture are in nanoseconds. So if we take this into nanoseconds, that's a lot of nanoseconds. So this stuff is really, really fast. So don't worry when I tell you it takes 5 times as long to do something on one version as the other, because it's really fast still. But it's good for you to know. All right. So again, do not panic. Remember the clock speed of the Nexus 5, which is what I used to do most of my testing, because I wanted something that could run KitKat as well as run L&M, is about 2.3 gigahertz tops with 4 cores. So that's like billions and billions of instructions. I know I'm like sounding like Carl Sagan here. So we're talking in very small micro benchmark terms. Now, Android internals is this kind of thing I'm working out. I want to see what you guys think of it. So afterwards, we'll have a quiz. And it really is about the unique voyages of discovery we can take in an open source platform like Android. So the idea is not just to understand how to code Android, but understand how it works so that when you run into problems, you have a better idea of actually what you're dealing with. And we're going to do it kind of this way. We're going to actually test our assumptions. We're going to benchmark. We're going to look at source code. And we're going to debug, even in native. So this voyage once takes us into the land of optimizations in art. If you saw my talk yesterday, I got a bit into that. But this time, we're going to be a bit more pragmatic, because we're really going to talk about how the world of JNI has changed as we've moved from a world of Dalvik to a world of art. But I'm getting ahead of myself, so let's talk about native code. Most of you guys have actually done native code. But I'm talking about code written using the NDK. And we're talking about primarily C and C++ code that interfaces with the Android runtime using JNI. Here is a really, really abbreviated architecture diagram of what this looks like. Applications written with the NDK take the form of these DEX classes that execute on the Android runtime. They interact with system libraries by the SDK framework classes. And SDK application code is written in a language like Java that the runtime can support. So the Linux kernel is written primarily in C and C++, and so are the system libraries. The framework and the Java runtime call into these libraries using the Java Native Interface, or JNI. Now, the NDK essentially allows you to write a dynamically linked native library. But it can't run directly against the system libraries because these ABIs or APIs aren't stable. So the purpose of the NDK is to give you a stable application binary interface to run your own compiled code against that provides access to only the most critical OS features, so the platform can still continue to grow and expand and change how they implement things and be awesome, but your application code is talking to this through this ABI. It's all important stuff. And that's what it looks like. Boom, your application code now talks to your library, which is going straight to native. Let me talk to you a little bit about the history of the NDK. The original first versions of Android did not even have it, but we got it in Cupcake. And we've been slowly expanding it ever since. So you know, in the first versions of it, you got a C runtime, really minimal C++ support, zlib compression, logging, networking, dynamic linking, some math. That's not a lot, but enough. We then added graphics. So the first version couldn't even talk to OpenGL. But we added graphics there. And you know what? The longest part about the slide was actually trying to find all these images again. It's like, when have I used the slide with these images? And then Gingerbread really expanded things. Gingerbread got much more serious about gaming and multimedia. So we added our native application API. So you can actually build, that was the first version of Android where you could actually build a native application without needing to use any Java whatsoever. And then, and also sound, which was really cool. Like OpenSL was really nice to have. We continued to evolve it. An ice cream sandwich, we added the OpenMax AL media layer. Not many people know this, but you actually can access RenderScript directly from the NDK as of KitKat, and it's pretty cool stuff. It was a long request, and we also did a bunch of graphic stuff here. That's why these aren't in order, but in Jelly Bean MR2, we added ES3, and in Lollipop, we added 3.1, as well as 64-bit support. So that's pretty cool. So let's talk about some assumptions. So our assumptions are basically to follow the suggestions at the FastJNI article. If you have not read this article, it is the gospel for looking at how to deal with JNI on Android. But do they still make sense today? We haven't updated the article since we shipped ART. So here are the basic things you have to do, okay? Absolutely critical when you're trying to make JNI performant. One is you're going to cache field and method IDs, and you're going to do it intelligently. Two, you're going to get strings in a reasonable way, and you're going to copy things in native. These are the only 3 real tips we gave, but I'll go more into details. So how did we benchmark this? We actually used something called Caliper. Now, how many of you actually have ever heard of Caliper in this room? No one. That's good. One person, sorry. I had never heard of it before doing this, but I was interested in doing benchmarking. And it turns out, if you actually look at AOSP, we have caliper tests checked in. This is actually how we benchmark the VM ourselves. And we use this thing called Vogar. And if you actually look at what's checked into Vogar, it's a really ancient version of Caliper. I'm hoping someday we actually update that. It would have made my life a little easier. But Caliper is a really cool framework for running micro benchmarks. All right, so let's get to the first thing. This, if you haven't used NDK before, is how you access a class from native code. So once you have the class, and I'm passing this class in from Java, you can see JClassType. That is actually the class information. And then I can simply call getFieldID with the name of the field, the type of the field, so in this case integer. And then finally, I can call GetIntField to actually pull the value. So that's how we actually access an integer that's inside of a Java class from native code. All right, so the first suggestion, which is a really, really good one, is to cache field and method IDs. And here's why. Those field and method IDs are just numbers. They don't actually change once the class has been loaded. And if you want to be really, really good about when you actually grab them, inside of the static initializer of the class in Java, you can actually call some JNI code. In this case, I'm calling native init. And inside of native init, really should have been named native init now that I look at the slide, but that's OK. You can see I'm getting that field ID. And that field ID will be good as long as this class is loaded. So that's pretty awesome. I don't have to think about it. I'm just storing it in a little variable there that's associated with my native class. All right, so let's talk about performance. So here is how it benchmarks on a Nexus 5 running KitKat and Marshmallow. And you'll notice something. ART takes longer. That's going to be, in general, a common theme. ART is more complicated than Dalvik in general. And so it's even more important today than it was initially to cache these things, because devices are running faster, and ART is already faster at doing most things. So you'll even notice this maybe a little bit more than even these benchmarks should say. So let's look at the code and try to figure out why this is faster, or slower, I should say. And the really key thing is this thing here, this scoped JNI thread state and scoped object access. This is why JNI actually does not run at lightning warp speed. And that's because every single thread in Android can be in one of two states. It can be in running state. That's when it's, or actually can be in more than that, but two states that we care about. It can be in running state. That's actually when we're in the Java virtual machine and we're actually executing stuff, and then it's access to all that great, sorry, I should say the runtime. It's not, we do not have a Java virtual machine in Android. You can strike that from your memory. The Android runtime, that's when it's in there, or it can be in the non-running state or native state. So when we're actually accessing a variable like this, which is an int field, all of these are variables that are inside of the runtime, we actually have to switch the state of our thread in order to do that. And that means that we're doing a whole bunch of synchronization. And that synchronization is expensive. It's expensive on the order of about 300 nanoseconds. Now, to give you some context, because 300 nanoseconds is a really small number, the average function call, an average function call in ART is about 5 nanoseconds. In Dalvik, it's more like 10. So once again, we're talking about something that is really tiny number, but it's still like 60 times longer than a standard function call. So it's still something to think about. So let's look at our first scorecard. And yes, based upon our benchmark, caching field and method IDs is great for both Dalvik and ART. It's even better in ART. All right, so let's look at the suggestion 2 of this, which was use GetStringchars. Now, this was kind of interesting. So basically, as you probably all know, the standard for Java, which ART also follows, is to treat all strings as double byte character strings, UCS2. And this is important because we are in a world that's highly international. Single byte strings are kind of passé, et cetera, et cetera. Not to mention, as it turns out, the VM actually doesn't particularly have great instructions for dealing with bytes. So it's actually kind of nice to have these things in these two byte characters. Thank you. So the suggestion here is that rather than getting string UTF characters like we have there at the bottom, we actually call GetStringchars, which actually takes our string and gets us the closest to being a native representation of it that you could imagine. And we would expect this to always outperform the UTF equivalent, where it actually has to do a copy of memory. All right, so let's look at this. I took a 15-character string. I ran some benchmarks on this. And I was actually really astonished to see two things. One, as we expected, ART is actually slow, but it's actually much slower. And two, this was a real shock. If you look at those two blue lines, on a 15-character string, GetStringUTFchars actually performs faster than GetStringchars. How can that possibly happen? Because we already said GetStringchars doesn't have to copy the string. It doesn't have to translate the string between UTF-8. So something is happening to actually make on this very short string. It's actually faster to do all that copying and translation. So let's try a longer string just to see if I'm crazy here. So this is a string that's 100 characters long. And we see more of what we would expect. So GetStringUTFchars is now slower than GetStringchars. So the question is, why was GetStringUTF ever faster under ART? So let's look at some source code. So you can see here that GetStringUTFchars always has to copy. So what it does, it goes through, and it actually just goes to that copy operation. Well, GetStringchars actually has to go and check, well, can I actually avoid this copy? So it actually goes, looks at the heap, and checks to see if that's a movable object. And it turns out that's actually somewhat of an expensive call. So you can see here, there is this find continuous space from object. That just sounds dangerous. And what is this actually doing in real life? Well, it actually calls this, which has a for loop into it, which looks to find continuous spaces. So you can see already here, even though the VM is doing all of this work to try to avoid this little tiny 15-character, 30-byte mem copy, it's actually failing to run this particular case optimally. And so some point in between 100 characters and 15 characters happens to be the break-even point. What does this really, really mean? Is that unless you're passing very, very large strings around, do whatever the most convenient to you, honestly. It's not a big deal. If you have to do a whole bunch of crazy stuff in native code to actually make your code handle, two-byte strings, 2-byte characters, it might or may not be worth it. You'll probably want to look at actually profiling it. So here's our scorecard. So in general, yes, GetStringUTFChars is going to be faster for large characters, but not always. So I'll give it 3/4 of a star for art. Here's another suggestion that came out of there, which is use GetString Region. And this is kind of interesting. So here is what that looks like. So normally, if you want to copy a string into a native buffer, in this case, in my native, I mean just literally a buffer of characters, you're going to call GetStringchars, and then you'll memcopy it, and then et cetera, et cetera. And you'll see I'm also doing some memory deallocation here just to be fair on both sides. You can see it's actually several lines of code and several more accesses. Because every time you actually do something like GetStringchars or GetString Region, you're actually talking to the VM as well. Well, this is actually kind of cool. Sorry, you're talking to native code as well and to the VM. So this is kind of cool here. And you can actually use GetString Region, and GetString Region does the copy for you. That's kind of nice. Also, one thing I'm doing here, which is a nice little optimization, is I'm actually passing the length of the string into this. And that's kind of cool because, as it turns out, passing extra parameters into JNI is almost free. It takes literally on the order of a couple of nanoseconds for every single additional parameter you want to use. So that's awesome. And if I were going to actually query this string and say, give me the size of the string, that would be another 300 nanosecond round trip through the machine. So adding additional parameters is a great way of optimizing your JNI. So I thought I'd point this out. This is sort of a little minor optimization here. But if these things are what you're thinking about, again, you're trying to avoid round trips on both sides. You're trying to avoid extra calls into the VM, or into the runtime, as I should say, from native code. And you're also trying to do the other way. You're trying to avoid extra calls into native code from the runtime. All right, so what does this really look like after all of this? Well, it's kind of as you'd expect. GetString Region is way faster. You're avoiding doing an extra allocation. You're also, and so that's going to, in general, be good. Inside of, and you can also see in art, this is actually a lot slower than in Dalvik. And a lot is all relative. Again, these are all little tiny things. You might think after this talk that art isn't very fast. And I don't want you to give that I don't want to give that impression to you at all. In fact, art is scary fast at doing almost anything but this. So in almost any other way, it is going to blow away Dalvik. So do not take this as any kind of indictment against art. In fact, you can also, when I was asking one of the internal guys, it is also about why this is the case. Art actually was written in a time when we had multiple processor cores in the system. So when they started designing it and writing it, they were thinking the entire time about deadlock problems. And I would say that art takes an incredibly conservative approach to make sure that you're not going to have deadlock. And if you look in like the list of bugs on AOSP, you will find deadlock bugs in Dalvik, most of which have been fixed. But I think part of what you're seeing is the art team wanted this to be incredibly robust, and that's why you're seeing a little bit of this. So maybe in the future we can actually figure out how to make these even closer together. But that's what it's like today. All right. So another big win on art and a big win on Dalvik to use GetString Region. All right, let's talk about a problem that a lot of people have, which is sharing raw data with native code. And this is also part of this. Now, if you haven't figured this out by the talk, JNI calls are relatively expensive. And again, this is relative. We're talking about 5 nanoseconds for regular call to about 300 nanoseconds on a Nexus 5, to be fair, of a JNI call. So what is this? What are we really talking about? The overhead of a one-way call. Two-way call. This is a two-way call. So on Dalvik, our overhead was a little less than 130 nanoseconds. On ART, it's almost twice that. Good thing that devices are getting faster. You can see I've also benchmarked a Nexus 6P and a Nexus 9, both in 64-bit mode, and you see they're actually pretty fast. Even the Nexus 9 actually doesn't outscore Dalvik running on a Nexus 5 for doing these kinds of things. So JNI is expensive, and the real goal of all this, if there's any take back for this entire lecture, is avoid chattiness. Every bit of chattiness you add adds extra time. And a lot of that is stuff you don't even think of. So for example, let's say you're like, you know what, I'm going to avoid writing a whole bunch of code. Have you ever played with Unity? How many people here have played with Unity? So one of the ways in which you talk to Android from Unity is to use something called Android Java Proxy. And Android Java Proxy is really cool because basically it takes advantage of proxy interfaces and it creates a dynamic class essentially on the fly that's used to fill out some interface that you can then use to talk to a whole bunch of internal systems. What you realize is that by doing that, you are getting the chattiest possible interface into Android. And so if you're trying to do something over and over and over again, that's going to actually impact your performance. So for example, let's say you're trying to read bytes out of some class in Java, one at a time. You realize this is going to very, very quickly exhaust all of your CPU time on the main thread. So you really do have to be careful with what you do on this. And think about the interfaces you have between your native code and the VM. All right, let's go back over to this thing. So how do we actually deal with sending big chunks of data between native code and the runtime? And there is this cool thing called a DirectByteBuffer. Now, I don't know how many people have played with DirectByteBuffers here before. You pretty much only ever want to deal with a DirectByteBuffer if you're working in native code. There's really no other reason for them to exist, as far as I can tell. Although the VM might choose to not actually allocate this memory out of its normal page pool. So on some VMs, it actually might get you memory you don't normally have access to. But in our runtimes, it does not. So and you get this nice allocate direct. And then when you're inside of native code, you can just get an address to that chunk of memory and start writing to it, which is really cool. And there's no like, I want to free this. There's no like release address. It's one call. So that's nice and fast, right? In theory. So this is what this looks like when you're using DirectByteBuffer. So let's look at the performance. Again, we're looking at benchmarks there all the time in these things. Keep me up sleepless nights doing these. And what that actually looks like. And as you can see, once again, this is a very, very slow access because DirectBuffers actually involve even more synchronization. And so we're talking about something that on ART running a Nexus 5 is almost in the 600 nanosecond range. So you really want, once you actually grab this, the answer is you really want to use it for something. If you're using it to pass an integer, not a good idea. You want to actually use it to pass lots of data. All right, but there's another side to this. Once you're inside of code that's running on the runtime, what's the performance of ByteBuffer versus DirectByteBuffer versus regular ByteBuffer? So let's take a look at that. What? Okay, now let me just back up a little bit here because you're seeing something really, really strange here. You're seeing that, first of all, Dalvik Nexus 5 DirectByteBuffer is the slowest call by a substantial amount compared to all of these other calls. Okay, it takes 300 nanoseconds. The other thing you're noticing is a DirectByteBuffer is way slower than a standard one, which is backed by a standard byte array in Java. So once again, two things that are kind of weird. And whenever we see really weird stuff like this, other than scratching my head, it is time to go and explore some code and try to figure out why that's the case. All right, so here is what actually happens when you do allocate and allocate direct. You actually get a different class. We're using polymorphism here. It's awesome. You either get byte array buffer or DirectByteBuffer, one of the two. Okay, and as you can see, byte array buffer is backed by an array. And DirectByteBuffer is actually backed by this class called memory block. All right, so, and here's how we start reading the integer. We use the call GetInt, and in byte array buffer, it's pretty standard. It actually goes into another class called memory, peek int, And inside of memory block, we have an extra bit of indirection. We actually have to call into the block class, which calls into memory.peekInt, but a different call, because that peekInt is taking a backing array, and that other one is taking an address plus offset. And yes, you are actually looking essentially at pointer arithmetic inside of the runtime right here. Not something you see very often. So what does this mean? Well, when you're actually looking at how this is implemented, if you try to find the source code, this is what you'll see. You'll see probably the most classic implementation of how to pull data from an array and get it into an integer that you see inside of the byte array class. And inside of memory block, it actually calls into JNI. All right. So this is now remember, let's go back to this graph here. So we saw that ART is way, way faster than Dalvik at doing this. And yet, we just demonstrated, looking at the source code, that it's actually calling into JNI. So that's really weird. Why is it so much faster? All right. So once again, here's what actually happens inside of that native code. But that really doesn't matter, because as we've shown, almost all of the cost of this operation is going to be in synchronizing between the different thread states, between the two VMs. So it turns out that ART is actually doing a little trick. And that is, when it actually declares the method, it's declaring it with this little exclamation point on it, which is a flag to the VM that says, well, this is a dangerous function. Actually, it's a flag to the person coding it that it's a dangerous function. It's a flag to the VM saying this is a very non-dangerous function. It's not going to try to do anything in Java. It's not going to last for very long. So let's not actually go through and change the state of the thread at all. Let's just run this code as quickly as possible. So once again, this is how long it actually takes to read that integer from a ByteBuffer. Now, it's still about half the speed, even on ART, of our standard ByteBuffer call. Even with all of that, even with this fast switching, and that's because if you actually go and throw this into a debugger, you realize that that whole statement about where it's using lots and lots of shifts in order to do it is actually not getting run at all. It's actually an intrinsic. And so that's how this is speeding it up. And also, even if it was running that code, ART is just really fast. It's really, really fast. And as it turns out, there is some overhead in doing even this fast JNI call, because it still has to set up the call stack and do all the other things that it would have to do to actually switch from running in the runtime to running native. And that takes about 50 to 60 nanoseconds, according to my benchmarks, just to do that in FastJNI. All right. So is there anything we can do to avoid having to make a JNI call for every single int we want to read? It turns out there is. We can actually get it all at once using something like this. So we can get buffer, we can allocate an array, we can wrap that in a new ByteBuffer, and then we can get that. Okay, and we have to fiddle with the position, because otherwise there's an overflow. There's no fast call to actually just give me the contents of that buffer that'll actually work. So believe it or not, this is what you have to do. And what does that look like if you do all of that? Allocations, and this is even including deallocations and stuff like that. And the answer is, of course, it's pretty slow. It's really, really slow on Dalvik. You can see this is where you're starting getting into multiple levels of optimization here. But if you're going to be moving a lot of data around, big chunk of data, and you're going to be accessing that from inside of the runtime, then yes, this is a strategy that might make sense for you. If you're for example, one of the things you might want to be doing is using flat buffers to move big C structures to the runtime. And how many of you are familiar here with flat buffers, first of all, when I say that? All right, so flat buffers are really cool. They're an open source project that my team created. And it basically allows you to do really, really efficient translation from stuff that's coming in either from disk or from network into structures that you can use. It is about as efficient as you can get, given the amount of flexibility that it has. It's actually very similar to protobufs, if any of you have used that, except that it's designed from the start to run on mobile and to run really, really fast. So So if you're doing something like that, you might actually get some performance out of this. All right, so now since we have a little time, I wanted to show you just a little bit of how you use JNI in Android Studio. All right, so once again, how many of you here have actually tried doing this in Android Studio? Okay, so that's not an enormous number of people, but that's OK, because this is actually really cool. This made my life so much easier than actually trying to actually deal with the various things that go on in JNI. So here's a whole bunch of native declarations that are inside of my JNI benchmark class, and you can see the kinds of things you'd expect, like these byte array calls and string calls, and so let's say I want to add another native method. Okay, so I'm going to type native. Let's have it return an int. I don't have to call it JNI, but just for consistency, I'm going to call it JNI pass a bunch of stuff to native. And so we're going to pass, let's say, a string, a ByteBuffer, an integer, and a long, et cetera, et cetera. And you'll see a couple of things have happened here. Probably the most useful thing is that we actually now are compiling the native code and the Java code all in one Gradle build, which is really awesome because we can do stuff like say, hey, this function actually isn't found. We can't resolve this. So you see it shows up red. It knows that it's not in my native code. So here's the really, really cool trick. For anyone who's done a lot of JNI code, the ability to do this is awesome. I can do create function here, click on this, and now I have a native function that's been created inside of that C file. And this is really cool. First of all, it's also done some helper things for me. It thinks I might want to get this string, interestingly enough, into UTF rather than double byte characters. But hey, it's probably what your code wants. And it's also gotten the byte array elements for me, and it's released them at the end. Because if you're going to use, it's assuming you're actually going to want to use these things, and so it actually puts in that code for you. So this is really, really cool. And the best part is now when I go back to my benchmark class here, you'll see it's no longer red. It's actually done the compile, and we are golden. We are actually ready to now run that inside of this class. So if you haven't had a chance to play around with Android Studio and its support of the NDK, I highly recommend it. It's still a little bit of work to get your Gradle project up and running because you've still got to use the experimental version of Gradle, but you don't actually have to use the experimental version of Android Studio. It is now in mainline, so go check it out, play with it, and make sure that you're not making your applications that actually use the NDK very chatty. If there's anything you can take back from this entire lecture. All right, so I'm going to switch back into non-mirroring mode so I can finish all of the exciting slides that are left in my that are left in my presentation, which is really just this. If you need to get in touch with me, this is how you do it. I hope you've enjoyed the talk. I hope you learned a little bit. I have time for some questions. If anyone wants to stump me, this is a really good chance to do it, because you most likely will. But other than that, again, it's not that scary to use the NDK. It is really cool to use the new Android Studio stuff. And you just have to be cognizant of the kinds of performance problems you could create with it. And I hope you got a little bit of it from this. And also, once again, what's wonderful about a platform like Android, an open source platform like Android, is you can go and explore the code. You can actually understand how we solve these very difficult problems in many cases. And you can learn something and take something back with your engineering career and use it again. And that to me is half the fun of working in an open source project. I mean, wouldn't it be awesome if everyone could simply say, here's the reason why that doesn't perform well. Let's go look at the source code. And I think everyone should be able to do that. So I'm super excited to be able to work on a development project that actually does have an open source backend. So that being said, thank you very much for coming this morning. And I will take questions now. OK. I do not know. That is a really good question. You've now stumped me. I'm so embarrassed. That's okay. and yes? Uh-huh. Mm-hmm. So if it is like let's say you're doing like Java GetString critical, which would mark that as being in use. That will never be moved. That is fixed in memory. DirectByteBuffers are also fixed in memory. They can't be moved. There is a little bit of weirdness around that because if you look at the way they're allocated, there is a little bit of code that checks around moving them. But once you're actually accessing them, getting that DirectByteBuffer address, it is fixed in memory. So it can be moved, however, outside of that call. So once that call goes away, my understanding is that it can be moved. So again, it's protected for the lifetime of that call. I think that's a really good question. I think that's what I remember, and don't quote me on that one. I might be wrong. It might be always protected. But in looking at the allocator, there are actually two different kinds of allocation that can happen, and for very, very small, like less than 3 pages, it goes into the movable allocation pool. And for things that are larger than that, at least in the current implementation, it's not movable ever. So yeah, kind of yes and no. Yeah? It depends on whether or not you. So the question is if you're using a back end to deal with this data, are you better on and you're talking to C++ code? Ultimately, you need to get that data in your C++ code. Is it better to just use the networking services that are built in to the NDK, or is it better to actually use and do everything in Java? And there's kind of two questions that I have about this. Is the performance of your networking something you actually even care that much about? That's the first thing. If you're not on the main thread and you're processing some stuff in native code, you might not care that it's a little bit more expensive because you're not actually affecting the frame rate of your application. And you might be saving an enormous amount of time by actually using the implementations that are in Java. So as a general rule, you really want to look to see whether or not you actually care about that particular performance loss, I think, and then weigh it. Yes, for performance, you're going to do way better if you parse something in completely in native code, especially if you're not using it on the Java side of things. Then yeah, that would make sense. But the real question you have to ask is, what's the cost of that? What's the cost in terms of opportunity? How much more time is it going to take me? Is it really worthwhile? And that's with all of these things. That's what I say. If it's an easy optimization, like let's throw a couple parameters into a JNI call, by all means do it. Don't waste more time. Don't waste more battery. But if it's going to mean rewriting an entire library, then really look closely at it and say, how much am I really gaining out of this? Mm-hmm. Mm-hmm. So the question is about JNI versus using RenderScript. When does it make sense? So what's really cool about RenderScript, first of all, is that RenderScript is actually LLVM bytecode that gets compiled on the device. And there's some beautiful things you get from that. One is that it can be actually optimized for that particular CPU that's running on the device to some degree. There's certain kinds of optimizations you can't do from LLVM, but there's a whole bunch that you can. There's intrinsics that you can actually swap in and out. There's like peephole optimizations that are specific to actually how that particular device works. So that's one of the secrets of RenderScript, is that it actually can generate better code than the compiler can in some cases. Second thing is it's also running in a kernel. It's actually running in its own little tiny machine that is used to run massively parallel stuff. And it's really set up to do that very, very well. So if your problem space falls into RenderScript, something that's really helped by parallelization, and something that is and something that's also helped by using these intrinsics that you get from the LLVM bytecode, then by all means use it. But as a general rule, I would say that, again, you're looking at opportunity, time, and cost. If you're not seeing that it's a performance issue that's impacting you, it may not make sense to go through to that. The main part of the reason we have JNI is to be able to reuse all this crazy amount of C and C++ code that's out there. And so for me, it's like you always have to balance these things. But from a true performance standpoint, it is very possible that RenderScript will be the highest performing way to do certain kinds of operations, because it can just do a whole bunch of things that the compiler can't do because it just doesn't know enough about the system architecture. And then it really depends on how well the individual OEMs have actually managed to, or chip providers have actually managed to optimize the RenderScript compiler on their particular chipsets. So there's a lot of variables here. I wish there was a cut and dry answer. But what's great about RenderScript, the really cool thing you might want to use it anyways, even despite all of that, is because, as I said, the LLVM bytecode gets compiled on the individual system. So you only have to ship one copy of the bytecode. You don't have to use a dependency on the NDK. You don't have to worry about it bloating the size of your build with a whole bunch of different executables. And that by itself might be worth investigating RenderScript just for that one reason. Now, with 64-bit, I believe you actually do need to ship 64-bit bytecode, so it's not completely transparent to architecture, I think. I haven't actually tried this, but I vaguely remember reading that somewhere. Sure? So if you do mallocs and frees, it's separate. It's actually using a different allocator. It's using JEmalloc when you're doing stuff from the NDK, and you're using rosalloc when you're in the virtual machine. And the reason is that, and if you went to the talk yesterday, rosalloc is really, really good at garbage collecting in the background, and we're trying to avoid heap fragmentation by bucketing all of our memory allocations. JEmalloc is not trying to have everything cleaned up in the background. It doesn't have to be as parallelized. So it's a slightly faster allocator than rosalloc when you're in native. So yeah, they don't share space. It's been a long time a thing in Android that if you desperately needed to run something that couldn't run inside of the heap space that we give you in the runtime, you could add native code. There's other ways to do that too. You can run multiple VMs, like having a different by launching each activity into a different process. There's all sorts of ways of getting around this, even using ashmem as a last-ditch resort if you actually are completely out of all the memory we allow you to do that. But realistically, yes, they're entirely separate heaps. And yes? Oh, it's not that complicated. It's just that it's just that we've changed. So the reason I say complicated was probably not the right term to use there. It's actually it's mostly that we've changed the structure of the way the Gradle files look. So if you actually look at what we've done, we've added the concept of model into the experimental version of Gradle. Oh, sorry, you can't see. Let me mirror the display. I just did like the dumb Californian thing here. All right, so there, now you can see what I'm saying. So if you've taken a look at the build.gradle file here, you'll notice that we've added this concept of model. So now Android is not at the top, model is at the top. So basically you need to go through and restructure your Gradle build a little bit in order to take advantage of this. There are some pretty good things online. You also see like all the kind of standard things you'd expect to see in the old NDK build is there. You can actually add libraries here, and also turn on, static libraries as well as dynamic libraries here. So pretty basic stuff. You can see I'm not using any of this in that. This is also how you build different product flavors. So you see I'm building x86, ARM 7, and ARM 8. Actually, I'm building all, because I have all of these here. That's hilarious. But in any case, this is how you would do product flavors, and dependencies, again, just like normal Gradle stuff. So it's a little different in structure, but it's really not hard to set up once you've actually set it up. If you want, I can even show you debugging. It's really cool. I think, actually, I may not be able to show you debugging, because I think we're basically out of time. But if you want, I'll show you debugging. If anyone wants to come to a table out there, I can show you how the debugger works. So if two options NDK and Google Play, you can either upload each individual variant as a separate multi-APK chunk. Basically, those are all separated by version codes. Or your other option is you can put them all into one APK, and it will do the right thing when it actually launches the application. So you've got two options. It really depends how much native code you have and what percentage of your APK size it is. For some people, even having 6 flavors of their NDK libraries will only be a negligible amount of their space. For others, let's say you're running something really big and heavy like Unity, it has its own runtime and all sorts of stuff. You're definitely going to have to seriously consider distribute on Play. So multi-APK is really the way to go if you want lots of different versions. And native machine like that, and I highly recommend doing it. You use a translator to actually ARM code. It's pretty fast, but it's not nearly as battery efficient as x86 code. So I highly recommend doing an x86 build as well. One of the big things I hope that we do is make multi-APK even easier to use, because right now there's sort of a partitioning scheme we suggest, and it's a little bit more of a challenge to walk through the first time on the Play Store. So I'm hoping we actually make that better. I think I'm out of time though, so I can totally take questions afterwards. But thank you all for coming. I hope this was fun, and enjoy the rest of your barbecue.